Hello students, welcome to Veda Gate Academy. So in this session, I would like to tell you how the transformer is going to be operated under loaded condition. As we know, in the previous session, we have seen the operation of the transformer under no load condition. And in this session, I would like to discuss about the operation of transformer under loaded condition. So to understand this, what I will do is I am trying to simply, so I will close this switch. The moment if I close the switch, what will happen? We can say that the transformer is operating under loaded condition. To understand the entire operation, I am going to consider this is a alternating voltage. So I am going to consider this particular terminal is positive with respect to this one. Okay, this terminal is positive with respect to this one, and I will do the entire discussion with this particular assumed primary polarities. Okay, right. So the moment if I am applying a voltage at a frequency, let us assume for a moment, if you quickly revise the operation of transformer under no load condition, assume that the switch is open. So the moment if I apply a voltage at a frequency F, the primary winding of the transformer will draw a current called magnetizing component of current, and this magnetizing component of current is flowing through how many number of turns, guys? N1 number of turns. Because of this I mu which is flowing through N1 turns, under no load condition you are going to get no load MMF, which is equal to N1 into I mu. And this no load MMF will try to drive a flux which is called operating flux phi naught. Okay, and what is the direction of flux lines? Again, you have to use the right hand thumb rule. According to the right hand thumb rule, since we are dealing with a group of conductors, if you apply right hand thumb rule with the help of 4 fingers, my thumb should be in the upward direction. So the direction of flux lines will be in this direction. And assume that there is no leakage flux, since we are assuming it is an ideal transformer, and we will assume that the entire flux which is produced will be confined only to this transformer core. Okay, there should not be any leakage flux. So and this is my direction of main field flux or operating flux phi naught. Okay, so as we know the flux is a closure path, it will be completed in this fashion. So because of this operating flux which is linking with N1 and N2 turns, you are going to get induced EMF statically, and this E1 is called self-induced EMF in N1 turns, and mutual induced EMF in N2 turns. Okay, so that means as the moment if phi naught is produced, you are going to get induced EMF in the primary and secondary winding, and according to Lenz's law, these are produced quantities, and this is the reason behind or cause behind the production of this one. So these produced quantities will try to oppose this P1. This is what we have discussed in under no load condition. Now relax. Now what I will do is I will try to see the discussion, okay, with respect to loaded condition, so that we can able to get the feel about how the transformer is going to behave under loaded condition. So assume that the switch is in closed position. The moment if the switch is closed position, then whatever this EMF which will, okay, induced will try to drive a current, because we have connected the secondary winding of the transformer to a load. So my load will draw the current, right? So the moment if I switch on the supply to the light, tube light or air conditioner or a fan, so they will draw the current, right? So the motor will draw the current. Similarly, let us assume it may be load, can be anything. So the moment if I connect these transformer secondary winding terminals to the load, my load will draw the current. Now at this instant I cannot able to directly say the direction of the current through the load is in the clockwise direction or anti-clockwise direction. So we need to okay, we will be patient. Okay, please relax. Now we need to understand what is the direction of the current. This is one of the previous gate question. They have given the winding in this fashion, and they ask you to determine what is the direction of the current through the load. Okay, let us assume the load terminals are A and B. Is it from A to B or B to A? Now to understand that, again we have to apply Lenz's law. Right, relax. So the moment if this E2 is produced, this E2 is called induced EMF in which winding? Secondary winding. In generally, the subscript 2 represents the secondary side parameters, and subscript 1 represents the primary side parameters according to our standard convention. Right. So this EMF will drive a current I2. I don't know. As of now, I don't know what is the direction of the current I2. Okay, we'll see. Relax. Right. So the direction of current I2. So I2 obviously will flow through the load. Again, for the current there should be a closure path. So the current will flow through even these N2 turns, and it will complete the closure path in this fashion. Right. It may be flowing in this direction or in this direction. That we need to calculate. Right. So that we need to calculate here. So we need to understand that this current I2 is flowing through how many number of turns, guys? N2. Here I mu current is flowing through N1, we are getting no load MMF. And if this current I2 is flowing through N2 turns, you will get one more MMF. That MMF I can call it as secondary MMF, and this is equal to N2 into I2. Okay, and again air state will come into the picture. Why air state will come into the picture? Because whenever if current is allowed to flow through any winding or conductor, around the winding you are going to get magnetic flux lines. Here what we are doing, we are allowing current I2, through these N2 turns. Okay, so this, because of this current I2 which is flowing through N2 turns, air state will come into the picture, and one more flux phi2 will be produces. So one more flux phi2 will be produces. Now what is the direction of this flux? What is the direction of this flux? All of you please relax and please focus. So here, can I say phi2 is my producer quantity? Yes. Phi2 is my producer quantity. Yes. Now can you tell me what is the cause for the production of this phi2? So here if you apply, this phi2 is produced because of the secondary MMF F2. Can I say my phi2 will oppose this F2? No, because they are of different dimensions. Now this F2 is produced because of current I2. That means can I say phi2 will oppose I2? No guys, right? And this I2 is produced because of E2, right? That means can I say phi2 again will oppose E2? No, because they are of different dimensions. Now this E2 is produced because of the flux phi naught which is linking with these N2 turns. So the major cause for the production of phi2 is phi naught. So according to Lenz's law, this flux phi2 will try to oppose the changes in phi naught. Okay, so it will try to oppose changes in phi2. So my dear friends, so the phi2 flux produced in the secondary winding will try to oppose the main field flux phi naught. Opposition in the sense, if I say my main field flux is in the downward direction, the flux which is produced in these N2 turns because of the current which is flowing through N2 turns should be in which direction guys? Upward direction. So this is my direction of flux. The direction of flux what? Phi2. So this is my direction of flux phi2. If you understand what I'm saying, so since it is a curly field, it will close on its own in this fashion. So this is my direction of flux phi2. I hope you understand. Now the moment if this flux phi2 is produced, then can you tell me what will happen to the net flux available in the transformer core? So the net flux available in this case becomes what you are going to get initially, operating flux, and this flux phi2 is produced in the opposite direction. So the mathematical I can say phi naught minus phi2, but it is a not arithmetic addition, arithmetic subtraction. It should be a vector subtraction. We'll see those discussions later. Okay, so you are going to get phi naught minus phi2, right? This is the net flux. So can I say my net flux here is decreasing or increasing? The moment if this flux phi2 is opposing phi naught, I can say my net flux starts decreases. As the net flux starts decreases, what is the meaning of that? The amount of flux that is linking with the N1 turns also decreases. The moment if this flux, the net flux linking with the N1 turns is decreasing, then what will happen guys? As the net flux linking with the N1 turns decreases, my induced EMF in the primary winding also decreases. As induced EMF in the primary winding decreases, okay, we need to say that applied voltage has to be also decreases, because since it is ideal transformer, we are assuming that there are no losses, there is no winding resistance. If there is no winding resistance, if I apply simply KVL for this particular winding, I need to get the magnitude of V1 should be equal to magnitude of E1. But because of the net decrement in the flux, E1 decreases. As E1 decreases, according to this relation, I need to say V1 should be decreases. But because this is an ideal voltage source, right? So since it is an ideal voltage source, always the magnitude of the voltage and time period of this particular voltage will be always remains constant. Am I correct or not? So I can say V1 should be exactly equal to V1. As E1 starts decreasing, the moment E1 starts decreasing, why E1 starts decreasing? Because my net flux is decreasing. Why my net flux is decreasing? Because the moment if I connect a load across the secondary winding of the transformer, I am getting phi2 which will try to oppose phi naught. So net flux decreases. As net flux decreases, E1 decreases. As E1 decreases, V1 starts decreasing, but which is against to the principle, because it is an ideal voltage source. So what will happen here is, relax. Okay, relax. So what will happen is, the moment if I close the switch and if I connect the transformer terminals to the load, my primary winding of the transformer will draw one more extra current called primary load component of primary current. Here whenever if I am using the subscript, superscript dash, that represents the secondary side parameters reflections on primary side. So this is called as load component of primary current. So why I am using the term load component of primary current? Because this current will come into the picture the moment if I close the switch across the secondary winding of the transformer. across the secondary winding of the transformer. I hope you understand. Now, again, this current I1 dash is flowing. Let us assume this current I1 dash is flowing through how many number of turns? N1. Here I cannot able to directly say the direction of current I1 dash in this primary winding. Relax, I will tell you. So it is flowing through N1 turn. So you are going to get one more MMF. Okay, load component of primary MMF F1 dash, which is equal to N1 into I1 dash. And this load component of primary MMF will drive one more flux. Let us assume phi1 dash. This is called compensating flux or load component of primary flux. Okay, now can you tell me what is the direction of this flux phi1 dash? The direction of this flux phi1 dash is in such a way that according to Lenz's law, it will also try to start oppose the reason or cause for the production of it. Okay, so that means here the producer quantity, if you clearly observe here, is phi1 dash. Okay. Now, this phi1 dash is produced because of whom? F1 dash. Can I say my phi1 dash will oppose F1 dash? No. And F1 dash is produced because of whom? I1 dash. Can I say my phi1 dash will oppose I1 dash? No. And I1 dash is produced because of whom? V1. Right? So, can I say phi1 dash will oppose V1? No. Right? This I1 dash is coming into the picture because of whom? This current I2. Yes or no? Right? And this current I2, okay, will drive which flux? Phi2. So, according to Lenz's law, this phi1 dash will try to oppose this secondary flux. Okay, it will try to oppose this secondary or load flux phi2. So that means, can you tell me guys, what is the direction of phi1 dash? The direction of phi1 dash should be oppose, means in the sense phi1 dash should be in this direction. Yes or no? So now if I try to close these flux lines, so we are going to get the flux lines in this fashion. I hope you understand. Now, okay, so please relax. Now I will try to indicate the direction of the currents. Here, can you tell me, here, if you clearly focus at this point, I have told you that the direction of current I2 in the secondary winding is in such a way that it produces one more flux phi2 which will try to oppose phi0. In order to show the opposition of this phi2 on phi0, I have shown this phi2 in the upward direction. If this phi2 is in the upward direction, can I able to know the direction of current I2? Yes, of course. I can easily know the direction of current I2. What I have to do? I need to simply apply right hand thumb rule. Here, what I know, what I need to calculate. I know the direction of flux, but I need to calculate the direction of current. For that, what I have to do? Here, I need to see whether it is a group of conductors or single conductor. It is group of conductors. Now, what I have to do? If I am assuming these are group of conductors, I have to use thumb to represent direction of flux, whereas my four fingers are used to represent the direction of current. Yes or no? Here also, what I have done? I know the current I mu, which is flowing here. So, from that, I can got the direction of flux by using thumb. But here, I know already about the thumb information. That is the direction of flux lines. Phi2. Here blue color represents phi2. Okay, so the direction of phi2 is in the upward direction. So my four fingers are showing, okay, for this winding towards right hand side. So that means, can you tell me guys, what is the direction? The direction of current I2 in the secondary winding should be in this fashion. Then only if I apply right hand thumb rule, my flux phi2 should be in the upward direction. So that means if you clearly focus here guys, what will happen? So the flux, the current I2 is moving in this direction. The current I2 is moving in this direction. Is it in clockwise or anti-clockwise? Clockwise direction. That means I can say the current I2 is flowing from A terminal to B terminal. So since it is a load, the moment if current is entering into the load, according to passive sign convention, I can say this is positive terminal with respect to this one, and this load voltage is called as V2. And according to the same passive sign convention, this acts as a source. For a source, always this terminal should be positive with respect to this terminal. Then only from the source the current will be generated and it will flow through the load. So this is the way you need to determine the direction of current I2 in secondary winding. Now can you tell me how to determine the direction of current I1 dash with the help of phi1 dash? Okay, where my phi1 dash direction is there, my phi1 dash is in which direction? In the upward direction. As phi1 dash is in the upward direction, this is the direction of phi1 dash. So I need to use the again right hand thumb rule. So my thumb is in upward direction, phi1 dash, my four fingers are in this direction. So the direction of current I1 dash is in the same direction as that of I mu. Okay, the direction of current I1 dash should be in this fashion. So this phi1 dash will try to oppose phi2. Until which point it will try to oppose phi2. So the meaning that the moment if the during steady state period this phi1 dash is also going to be appear. So it should be added with phi0 or opposed. So this is minus symbol means this becomes plus symbol you are going to get. Because these two fluxes phi0 and phi1 dash both are added and phi2 will be subtracted from the combination of phi1 and phi0. Right? So what will happen? So here the moment if phi1 dash is coming to the picture, my net flux starts increasing. As net flux starts increasing, the reduction of the EMF also starts increases, right? So as the reduction is decreases, then what will happen? My E1 will be almost V1. So that means in order to make V1 should be equal to E1, the net flux available in the transformer core should be same as under no load condition. That means my phi1 dash not only oppose phi2, but it will also nullify phi2. So that means it will completely, this phi1 dash will be completely cancelled with phi2. The moment if this phi1 dash is completely cancelled with phi2, the net flux available will be same as no load flux. As no load flux is linking, my E1 magnitude is exactly equal to V1 magnitude. So that means under loaded condition, automatically my transformer will draw, primary will draw extra component of current, which is used to nullify the secondary flux, which is created because of application of this load. Are you following what I am saying? So that means the point conclusion what I would like to say here is the net flux available in the transformer core under loaded condition as well as no load condition is both are same. So that is the reason transformer is considered as a constant flux device. What is the meaning of constant flux device? That means it is not meant that my flux is time invariant. Here the flux is time varying. The meaning of the transformer is constant flux device in the sense that the amount of flux available in the transformer core will be remain same under no load as well as loaded condition. Under no load as well as loaded condition. So this is how we need to determine the direction or polarities of secondary current and induced EMF in the secondary side. Now I will give a simple task to you. Okay, I will give a simple task and try to apply, okay, whatever the knowledge you have gained for this particular transformer core, and tell me what is the direction of the polarities of induced EMFs. Okay, so let us assume that this is my primary winding of the transformer, which consists of some N1 turns. Okay, and it is connected to what? Source, and assume it is connected to the source. And this is my secondary winding of the transformer. This is my secondary winding of the transformer, and it is connected to some load L1. Right. Now my question is, okay, so my question is, can you tell me what is the direction of the current in the load A? Okay, load, is it flowing from A to B or B to A? And can you please tell me what are the polarities of induced EMF? Okay, polarities of induced EMF and load polarities. This is the previous gate question. They have given in this fashion and ask you to determine what is the direction of the current in the load. Is it from A to B or B to A? And what are the polarities? Here, let us assume this is M and this is N. Can you tell me M is positive with respect to N or M is negative with respect to N? This is what they are asking in the previous gate question. Now, if I am showing here, are you finding any difference in the winding? That means sense of winding. Sense of winding in the sense how I have wounded the winding on the secondary side and the primary side. If you compare the previous diagram, this is my previous diagram. Here if you observe on the primary side, I have wounded the winding above the core, below the core, above the core, below the core. Whereas here first, here what will happen? Above the core and coming below and above the core in this fashion. Whereas if you observe in this question, primary side sense of winding is same as in the previous diagram, but secondary side sense of winding is completely different. Am I correct or not? Secondary side sense of winding is completely different. Now, in order to determine here, what extra information they have given is this terminal is positive with respect to this. Now, the same thing. What will happen first initially? IME will come. This IME will flow through how many number of turns? N1. Because of this one, what will happen? You are going to get flux. Okay, the direction of flux should be in this direction. This is my direction of operating flux phi naught. And this flux phi naught will be, okay, so let me completely draw this one. So this is my direction of operating flux. Because of this operating flux, what will happen? Induced EMF in the primary and secondary winding you are going to get. Right? Am I correct? E2, E1 and E2. And this E2 will drive a current I2. I don't know the direction of current I2. The current direction I2 will be in such a way that it will produce one more flux which will oppose the main field flux. That means opposition in the sense my flux, operating flux phi 2 should be in this direction. This is my secondary flux, should be in this direction. Now, in order to satisfy this right hand thumb rule, what will happen if the direction of flux is in this direction, direction of current I2 in the secondary winding should be in this fashion. So that means if you see the sense of the winding, what will happen is the current will flow in this fashion. Okay, so that means the current will flow in anti-clockwise or clockwise direction, anti-clockwise. So what will happen? This current will flow in this fashion and it will come below the core, above the core. above the core, above the core, and above the core, and the direction of current will be in this fashion. Since the current is entering B terminal, so B terminal will be positive with respect to A terminal, or I can say M terminal is negative with respect to N terminal. This is how we need to identify the direction of the current, whether it is clockwise or anti-clockwise, and the polarities of induced EMF in the primary and secondary. I hope you understand this, right? For suppose, if I extend this concept to one more winding, for suppose instead of two winding transformer, if I wound one more winding in this fashion, if I wound one more winding in this fashion, and here if I connect some more load, one more load, it may be a pure resistor or inductive or pure capacitor or combination of those things. Now can you tell me what is the direction of that polarities for this one? Let us assume these are the terminals C and D. Apply the same principle. Here you need to see with respect to which flux, operating flux phi naught. With respect to operating flux is in this direction. As operating flux is in this direction, the flux produced because of this particular load, okay, load current should be in which direction? In this direction. Red color represent operating flux. So this, let us assume phi 3, right? So the direction of phi 3 should be in this fashion. If I want to get flux should be in this fashion, my current has to, okay, current has to move in this direction. Are you following? So that means the direction of current should be in this way. Then only what will happen here, we are going to get the direction of flux. Phi 3 should be in this direction. So can you tell me, this is my direction of current, yes or no? So this is the direction of current in the second load you are going to get. So obviously this terminal is positive with respect to this terminal. I hope you understand this. So this is how we need to determine the polarities as well as the direction of secondary current and polarities of secondary induced EMF with the help of Lenz's law. So this is about the brief idea about the operation of transformer, okay, transformer with loaded condition. So the conclusion what we are getting from here is always transformer is considered as a constant flux device, and that means the amount of flux available in the transformer under no load as well as loaded condition will be remains same, and this process will be obtained. This statement, whatever the statement I have given, will be valid under steady state condition. Okay, once if the transformer reaches to steady state period, that means in control system we have learned about when the when any circuit will reaches to steady state. After, in general, after 5 times time constant, any circuit will reaches to its steady state response, right? So once if the transformer reaches to steady state, I can say that the amount of flux available in the transformer core will be remain same as no load flux. Okay, so this is about the brief idea about how to determine the direction of flux lines, okay, direction of secondary current as well as the polarities of induced EMF for the transformer under loaded condition. So I hope you have enjoyed this session and you have learned some new points, and okay, so in over the classes during the period, we will try to discuss about more interview questions in transformer. Okay, there are some few interview questions. For suppose if you are taking a mission, electrical mission, what it will do? It will try to convert either electrical form of energy into mechanical form of energy or mechanical form of energy into electrical form of energy. But the medium which is common for the conversion should be magnetic medium. You may have a doubt that in the interview they will ask simply, why magnetic field? Why can't we use electrical field? This is one of the standard interview question. Likewise, you may have another doubt that here I have wounded the winding on limbs rather than yokes. What will happen if I wound the windings on yokes? This is another beautiful interview question. Next, the other interview questions what we can able to face is, for suppose if I am taking the same transformer, once if the transformer is wounded, okay, once if the transformer is wounded, okay, laminated, insulated, and if you completely manufactured, then can we able to identify the number of turns of the primary and secondary winding or not? Okay, and can we able to say which is HV winding and which is LV winding? That means, for suppose after the manufacture of transformer is over, I have given to your hand. Okay, if I am giving it to your hand and if I am asking in such a way that, can you tell me which winding is acting as HV winding and which winding is acting as LV winding? Or can we able to say, okay, so in that fashion, for suppose if I am asking the same interview question, how to answer that? Likewise, there are beautiful interview questions are there where we can able to focus not only on this particular GATE aspirants, okay, we will try to even focus on how to crack the interviews in PSUs as well as in MTech for higher education. Okay, so this is how we are going to teach in our Veda GATE Academy, and you will definitely learn, okay, definitely learn all the missions, okay, all the missions from scratch level to up to the level where you can able to attempt GATE as well as engineering services. Okay, so trust me, we are with you, and always we are help to give service, better service to the students, and definitely you can able to success in your life once if you follow Veda GATE Academy. Thank you, all the very best.